Look closely at these Ugandan banknotes. For the 2024 to 2025 financial year, the national budget was over 72 trillion shillings. If you try to write out 72 trillion manually, you are forced to track 12 separate zeros for every single calculation you do. Now look at the opposite extreme. A single malaria parasite inside a red blood cell measures roughly 0.0000015 meters. Manually writing out all these decimal places takes up unnecessary space and makes it incredibly easy to accidentally drop a zero and ruin a calculation. This diagram shows the mathematical solution: indices. The large number, 5, is the base. The small number, 3, is the index, or power. It tells you exactly how many times to multiply the base by itself. Notice that this expands to 5 times 5 times 5. It is completely incorrect to multiply the base by the index to get 15. By using indices, economists and scientists create a powerful shorthand. It allows them to condense extreme values into a format that prevents catastrophic zero counting mistakes. This formula outlines the multiplication law of indices. When multiplying terms with the exact same base, you add the powers. If you ever forget this rule, write out the problem the long way. A to the power of 3 is 3a's. A squared is 2a's. Count them up, and you clearly have a to the power of 5. The division law works in reverse. When dividing terms with the exact same base, you simply subtract the smaller index from the larger one. 5 to the power of 6 divided by 5 squared gives you 5 to the power of 4. Let's test a common trap, a base raised to the power of 0. Look at these two equations. 5 squared divided by 5 squared is 25 divided by 25, which is 1. But if we apply the division law to that exact same problem, we subtract 2 from 2 to get an index of 0. Since both methods solve the same problem, 5 to the power of 0 must logically equal 1. These laws are reliable shortcuts for manual counting. Anytime an abstract rule starts to confuse you, expanding the equation into basic multiplication will guide you straight back to the correct law. Standard form applies these rules to base 10 to express huge or tiny numbers cleanly. This visual shows the strict structure required. The first number, a, must be exactly 1 or greater, but strictly less than 10. Anything starting with a 0 or a 10 is an imposter format and must be adjusted. Here is a wide view of Kampala. The city has an approximate population of 1,500,000 people. To put this population into standard form, we place a decimal point at the end of the number and move it left until we isolate a value between 1 and 10. The point moves exactly 6 places to land at 1.5. Because we are condensing a large number, the index on our base 10 is a positive 6. If we measure the length of an ant at 0.004 meters, we move the decimal to the right to reach the number 4. That is a shift of 3 spaces. Since we are dealing with a microscopic number less than 1, the power becomes a negative 3. Standard form strips away the visual clutter of endless zeros. By checking the sign of the exponent, you immediately know if you are measuring the scale of a city or the length of an insect. When dealing with standard form, you often need to round numbers to make them readable. Decimal places only count digits falling after the decimal point. Significant figures measure the precision of the entire number, starting from the largest value. Look at this diagram to understand the rule. Read left to right and wait for the light. You ignore all leading zeros until you hit the first non-zero digit. The 3 is your first significant figure. From there, you count every single digit, including zeros. The 0 is your second, and the 5 is your third. Let's test your understanding. In 1969, the population of Uganda was recorded at 9,500,000. Pause the video here. First, convert this number to standard form. Second, ensure the original number is rounded to exactly 2 significant figures. For standard form, the decimal moves 6 places left, giving you 9.5 times 10 to the power of 6. For significant figures, the 9 and the 5 are your first 2 digits. We check the third digit to see if we need to round up. Since it is a 0, the 5 stays exactly as it is, leaving the rounded number at 9,500,000. Leading zeros in a tiny decimal only locate the decimal point. They hold place value, but do not add actual measurement precision to your data. This diagram shows a multi-step algebraic fraction you would likely see on an exam. Start with the multiplication law in the numerator. The bases are exactly the same, so we add the 5 and the 3 to get 2 to the power of 8. Next, we apply the division law. We subtract the denominator's index, 6, from the numerator's new index, 8. That leaves us with 2 squared, which quickly simplifies down to a final answer of 4. This cheat sheet captures everything we have covered: the multiplication and division laws of indices, the strict boundary constraints for the standard form base number, and the traffic light method for locating your first significant figure. Applying these mathematical shortcuts correctly means you no longer have to struggle with massive national budgets or the invisible scale of microscopic cells. You can process extreme data with perfect accuracy.